Okay, so welcome period 8. This is a recording for Thursday, February 4th. So 8th period. Sorry I'm not there. Something came up, but this video is going to talk you through the homework that was due today. So that was worksheet 2. I'm going to talk through, how to do certain things on the calculator, specifically certain things we didn't do too much of, and then also just highlight, the general kind of path towards the answers on most of these. So that'll be part 1 of today, is we're going to go through this. Might take a little bit to do, but we're going to go through worksheet 2. And then I'm going to, or the plan for next time is to have worksheet 3 be due, and I'll try to set you up with that, maybe do 1 or 2 with you towards the end of this. We'll see how long this goes for. So for worksheet 2, the one due, right? This one, number 1, is the same as number 1 on, I think, the first worksheet, pretty much. They just changed up the equation. So to do part A, this is just saying plug in 1.2 for t. So it's just a straight up in your calculator, type that across and see what you get, right? Nothing to that one. However, B, C, D, and E, the rest of these are going to involve the actual graphing part on your calculator. So I'm going to show you that just one more time in case, I know we're kind of new to it. Try to get this in frame. I think that'll show up all right. So I'm going to type in to y equals this thing, right? Negative 16t squared and all that. So clear out anything that's in there. Negative 16 x squared plus 84x plus 60. So I'm just replacing t with x because that's what the calculator has. I'm going to press graph and see what I have. All right, so you could see a little bit of it, right? So we could see it's definitely, it's an upside down parabola, crosses there, and then the vertex is somewhere up here off the graph. So we want to be able to view that. So to be able to view it, what we're going to do is we're going to press the blue button. And actually, I'm sorry, not quite yet. We're going to press the window button because we got to adjust our window first before we find the maximum. We're almost always dealing with quadrant 1, so that'll be an x minimum of 0 and a y minimum of 0. If you recall on our graph, we were able to see both x-intercepts, right? So there's really no need to shrink that down or make that any larger, the x max. We could probably leave that as it is. The y max, though, that's going to take a little work, right? And here's how you find that. You're going to go to second and graph. Second and graph. And that gives you the table. And why we're looking at the table, the reason for that is we just want to see how big do these numbers actually get. I'm seeing 60, 120 something, 160 something, and then it starts going back down. So everything's staying under about 200. So I can go back to my window, go to my y max, type in 200, and with these window settings, we should be able to see, well, not the entire graph, but the part of the graph that we care about, the part that lives in quadrant 1, right? So there it is. So we need to find that vertex, and we don't want to do that by eye, obviously. We want to get the exact vertex, which can be done on your TI-84 by doing second, trace, and choosing option number 4, the maximum. Now, once you click maximum, it's going to ask you a series of 3 questions. The first one says left bound. There's your little cursor. So what you can do, you can physically move the cursor if you want to with the arrow keys so that it is clearly to the left of the hump, right? And then press enter, and then move it to the right of the hump, and then press enter. Or what I've been doing is saying, okay, my furthest left here is 0, so I could type that in, enter. My furthest right bound, which is over here, my window's at 10, right? 0 to 10, so I can type in 10. And then it says guess, that's my third question. I press enter, and it'll shoot up and calculate right at the vertex, right? So there's 2 ways to do it. You can move it manually with the arrow keys, that's fine, or you could type it in like I typically do. So you get your answer, but remember, you have to be able to interpret this. The y value is the maximum height this projectile achieves, so about 170, and that happens at about 2.625 seconds. So if I move this out of the way for a second, keeping those numbers in mind, that's the answer to part C. 170.25 feet is the maximum height, and it occurs 2.625 seconds after the object is launched. Now we need to do B, D, and E. D and E kind of go together. How about we do B first? We want to know, when is this thing at exactly 25 feet? I'm going to keep this window and graph how it is. Let's move this more into the light. But we are going to go back to y equals and keep that there and go to y2 and press y equals 25. So we're going to put a 25 in there, which is going to create a horizontal line through 25. And it's going to create an intersection with the graph there and also over here off in quadrant 2, but we don't care about that one. We care about this one. So we want to be able to calculate that intersection, which you can do with a series of buttons. Those series of buttons are the blue button and the trace button. And then instead of going to maximum like we've done in the past, we're going to go to the intersection, which is number 5, and press enter. Now there are only 2 objects on your screen. So it says first curve, I'm going to press enter. Then it says second curve, I'm going to press enter again. The reason I don't have to move them around or do anything is because there's only 2 objects. If you had more than 2 graphs, then you'd have to specifically move things around and tell the calculator which ones you were talking about, but there's no point here in doing that. So guess, and it's going to go and put a little star at that point, and it looks like at 25, that happens at 5.638 seconds. Right there. Okay, so that's how you would do it on the calculator. The process of finding the maximum and the process of finding the intersection on your calculator, remember I made 2 videos that you could view if you want to, if you're not, if you want to see this process done again, that are on Schoology in the Skill 4 folder. The last 2 items, D and E, they go together because we want to know, when does this thing, the object, hit the ground? So we're talking about, let's see, let me try to clear out of this. Maybe I'll do this. There we go. All right, so right down there, where does it hit the ground, meaning the x-axis? Well, once again, there's a button for that as well. We're going to hit the blue button and the trace button. We're not going to go to maximum. We're not going to go to intersection. We're going to go to option 2, the 0. Remember, 0 is another term for the x-intercept. So we're going to press enter on that. And once again, we get some questions that pop up. Left bound just means you're going to take your arrow keys and move the cursor. By cursor, I mean this little star thing here, so that it is clearly above the x-axis. So you see it's at the 0.5, like 54. That's fine. Press enter. It says right bound. Right bound means I want to go below the x-axis. So I'm going to move this down. Might take a few. Right there. Okay, so as you can see, my cursor is now at 5, -7. So it is below, so I can press enter. Press enter again. And there it is. So this thing hits the ground at 5.886 seconds, or 87 if you round it correctly to the thousands. So about 5.887 seconds. When it has an E like that and like -11, that's basically 0. It's a bit of a calculator, not glitch really, but it's just, it's doing its best. But this really means 0 because it's like 0.2, or it's like -2 times 10 to the -11 power or whatever. That's really what that means, which is like 0.1102. So it's basically 0. All right, so with that, there's the number I was just mentioning. And the domain, right? These are the numbers I'm allowed to put in. Well, all the way to the left along the y-axis, that's what happens at 0 seconds. So it starts up high, travels, hits down here at about 5.8 seconds. Anything after 5.8 seconds is going to give you a negative number, which wouldn't make sense because it represents height. Anything left of 0 wouldn't make sense because it would be negative seconds. That wouldn't make sense either. So that completes problem 1, right? I wanted to go through that one thoroughly. I won't do that for the rest of these. I'll just mention a few things here and there on the rest, but I wanted to make sure we could do every part of this, because if you could do every part of this problem, you should be able to do the calculator portions on the rest of these. Let's look at number 2. All right. It's another one of these that has a curve. This is a parabola, which I drew here with exact points. And you can get these exact points by plugging in 0, get 16, 1, get 15, 2, get 12, and so on until you get to 4, because 4 squared is 16, it would go to 0. So we're talking about a curve that lives between the x and y axis, and we want to make a rectangle that fits underneath the curve such that one corner's at the origin, one corner's on the curve, the other corner's on the x-axis, the last corner's on the y-axis. So the picture I drew is specifically for part B. If I have something that is 1 unit long, it must be 15 tall. So the area would be 1 times 15. But that's a specific example. Part C is asking in general. In general, how wide is this? Like I could have stopped at 1, I could have stopped at 2, 3, all the way up to just shy of 4, or 2.5, wherever, right? How could I call that distance in general? Well, that would be x. It would go x distance from the origin. So that's the width of this thing. How tall is this rectangle? And I'm not just talking about this rectangle, I'm talking about in general. The rectangle is going to be whatever this height is. Maybe there, right? All those points can be described by y. But we don't want to call it y, we want to call it 16 minus x squared, so it all has one variable. All right? So this is, I would argue, is the hardest part, getting this correct. And then D and E, you're just repeating the stuff we did in 1. You're going to put this in your calculator, and you're going to try to find the maximum height. This is going to be a cubic, so it'll look like an N, right? Or I think it's actually a backwards N, like that. And you're going to try to find the maximum right there. All right, so that's what D and E are about. We have another very common problem with number 3. You have 1,000 yards of fence along the river, and you're building the fence on 3 sides. We have an X, and then some length over here, right? So how I found this length of 1,000 minus 2x is I recognize that I have 1,000 yards of material. I'm going to use up x and x, or collectively 2x worth of material for the sides. So what's left over is going to be 1,000 minus whatever I used for the sides, and that's how long the long part, the long side would be. I don't need a fence along the river, so that is it. All right, so that answers part A. How long would this be? 1,000 minus 2x. How about the area? Well, it's a rectangle, so width x times length 1,000 minus 2x. This will be an upside down parabola when you put in your calculator. Part C, you don't need to do with your calculator. How you find these numbers of 0 and 500, because we're talking domain, is we look to part B. This is factored form. We got a single term and we got a 2-term thing, a binomial and a monomial. If this is set equal to 0, if this a of x is 0, well, that means how do we make that term 0? Well, just 0. How do I make this term in parentheses 0? 1,000 minus 2x set equal to 0 would be 500, would be what the x would have to be. So 0 to 500. Notice these are not underlined. The reason for that is you can't include 0 or 500 because if you included 0, you would have a no rectangle, right? You'd have a width of 0. Wouldn't make much sense. You'd have just a 1,000-yard line. Same thing with the 500. If you used 500 on that side, 500 on that side, you'd have an open rectangle, right? You'd have 2 short sides and no long sides, so that wouldn't be good. That's why it's not underlined. But on problem 1, those were underlined because it dealt with time. Because 0 seconds, that makes sense. When it hits the ground, that's a certain time, so that makes sense. But in general, if it's a time problem, you underline it. If it's a length problem, you don't underline it. And then D and E, they come from plugging part B into your calculator. Now these numbers are going to be rather large, right? This is going to be way off your calculator screen. You're going to have to find this, and this is really up there at 125,000, right? But that's why you look at the table, right? The table, second graph, right? Look at the table after you plug this in and see how big the numbers are in general. Like, are they in the hundreds? Are they in the thousands? Are they in the tens of thousands? These are in the tens of thousands because that's 125,000 yards. So we'd really have to put that Y max really high up there, okay? And same thing with your domain, right? The domain, the X min is 0. The X max is 500. Your Y min is 0. Your Y max is, again, you look at the table and just give it a guess, right? If it's in the tens of thousands that these things are getting up to, start high up. Maybe start at 1 million for your Y max. That might be a little too high, bump it down to 500,000. And then you could probably see it pretty well from there, but you could even go further down if you need to. Okay, so very common kind of problem though. Down over here, this one's heavily related to the previous one because it is a rectangle, but there's one difference. You have 60 feet of material instead of 1,000. That's actually not the main difference. The main difference is you have all 4 sides of this rectangle instead of just 3. So if I called the width x, x, and x, well, the long side of this rectangle would be 60 minus the 2 x's that you used to create the short side, and that will be the material you have left for both sides, both long sides. 60 minus 2x is how much material you have left for both the long sides. But the reason I divide it by 2 is because if I just want a single one of those sides, all right, I got 60 minus 2x for both sides divided by 2. That's why the 2's there. And you could leave it like this. This is perfectly fine. Someone in an earlier period said they wrote 30 minus x, which is perfectly fine because that's what this is reduced down, right? You could divide the 60 by 2, 30, 2x by 2, x, and you're done, right? So to get the area, it'll be x times this long side, and you'll get either that or this. And these 2 items are the things you're going to put in your calculator. One or the other. You don't need to put both because they're equivalent, and your calculator doesn't know the difference. Now, for the domain, this is something you would get without the calculator as well. You could look at either one of these and say, okay, I got 2 factors set equal to 0. So what would make this thing 0? 0 would do that. What would make this thing 0? That binomial? 30 would do that. All right, and again, they're not underlined because you can't have a width of 0 and you can't have a width of 30 because if you use 30 there, you just ran out of material. You have 2 short sides and no long sides, so you don't have a rectangle. I would argue BC, right? This stuff is like the hard part, and then you just plug it in. Plug this in your calculator, part B, plug that in your calculator or that, same thing, and see what the maximum is, right? Go through that maximum process. This one's a lot lower than the previous one, so you can, the answer's in the hundreds, so you want to drop that Y max from whatever you did in part E there lower because this thing's only at 225. This would be the Y coordinate of the maximum. 15 would be your X coordinate. So 15 times something is 225. And that something also happens to be 15. This thing's actually a square. That's the biggest area you could enclose as a square. Oftentimes it's a square with these problems, depending what they're asking. All right, so that's how that goes. And I'm not doing the calculator portions because it's basically a repeat of the first one, right? So, and if you need help with that, you could look at the tutorial video, or if you want to do it with me, like through Zoom, right? One morning, just shoot me an email. We could have a TI tutor session or whatever. I think there's one more problem. It's number 5, also heavily related to the previous 2. So they say, I believe, 60 feet of material, same as part 4, the previous problem, but they're mixing it up and saying, once again, this third side does not need to be constructed. It's a building. So that's a three-sided rectangle again. So notice the difference, right? I use up X material there, X material there, and we're going to get 60 minus 2X material here. I don't divide it by 2 because I don't have to share this material with this side because there's a wall there that's already built. All right, my area here, width, length, multiply them together. So this is a quadratic. It'll be an upside down parabola. 0 and 30, this is the same answer as the previous problem because factor there, what makes that 0? Factor there, what makes that 0? 0 to 30. Not underlined, same reasons. You can't have 0 width. And you would expect this area to be bigger than the last one because you have the same amount of material, but you don't have to waste any on this side, so you can build a bigger area. So be 450. The x coordinate it would give you would be 15. So 15 times something is 450. That something is 30. So this would be your x coordinate. This would be your y coordinate. All right, so that's how that goes. When I return on, I guess it would be next Monday, if we need to go over any of these, not a big deal. Again, if you want to meet in the morning through Zoom, that's also fine. I'm pretty open, usually like around 9 or 8 o'clock. So just let me know. I know this is a difficult skill, and I do not like to miss school, although it seems to happen quite a bit this year. So I do apologize about that. All right, so that's the first part of kind of the day here, was just to go through this. I'm going to be posting this answer key online so you could view it, but obviously won't have the commentary with it. So, maybe that's how you'd prefer it. But if you need any of that, you could always, pause, rewind this video. The second part of today, and what the goal is kind of going into next time, which for you guys would be next Monday, would be I want to see if we can complete and turn in worksheet 3. So let me get this going over here. All right, so on Schoology. Oh man, I'm not connected to the Wi-Fi here. 1 second. Hirsch Wi-Fi. Password. 1 second here. We're highly secure at Hirsch House. 1 second. All right, hopefully that's it. All right, I think we're in. We just hacked the mainframe. So we're going to go to Schoology. Let's refresh all this business. Skill 4, and again, so the next time the goal is to get worksheet 3 done. Let's take a look at some of these problems, see what we can do here. All right, so it should look like this. And obviously feel free to pause the video to get yourself gathered up with this. So calculator required, right? So it starts off, I think there's only how many problems here? We got 4. All right, 4 problems. Maybe I'll do the first 2, and then you guys see if you could do the remaining 2. I think that'll be the plan, okay? But, if you want to go for it first, like pause it and then try it, and instead of going through it with me, that's fine, and then look, and then play and see if you get the right answer. You could do it that way too. But let's take a look at this stuff here. So we have throwing watermelons off a roof here. What is the initial height of the watermelon? Well, initial height means time equals to 0, right? So when t is equal to 0. Well, you can kind of see if you were to plug 0 in there and there, you would be left with just 95. So 95 feet. Easy enough. What is the height of the watermelon after 2.5 seconds? That would be a matter of plugging in 2.5 for x. -16 2.5 squared plus 47 times 2.5 plus 95. And this is what you're going to be putting straight across in your calculator, right? So you just type that in exactly as it appears. And if you do that, let's see, did I do that earlier? I think I did. 112.5 feet. All right, so those are kind of the little kind of amateur problems there. Nothing too crazy, not using your calculator very heavily. But really, after that question, it's going to be diving a bit more into your calculator functions, like the graphing aspects and all that. Right, because they're saying maximum height, when is it exactly 20 feet off the ground, when does it hit the ground, what's the domain? All of that's going to come from graphing this thing. The domain is a little hard to do on this one without graphing it first, so that one I do include in there. So let's put this in our calculator. Move this to the side. Get the TI in frame. And let's type what the problem was, which was negative 16x squared plus 47x plus 95. Okay, so we have that in there. And we're going to press graph. All right, that doesn't look too bad actually. This is whatever window I had previously. So let's see, I had the Y max at 200. Well, let's take a look at the table. Second table. Let's see how high up this thing gets. Yeah, so we're talking somewhere around 130. So, I mean, we could change it if we want. If we want to drop the ceiling a little bit, we probably could. Let's go 150. Everything else should be pretty adequate. All right, so there it is. Maximum height, right? So we're talking the vertex. So this will be another little tutorial in how to do that. So if we want to do the maximum, we're going to do second, trace, and we're going to go to the max button. All right, the left bound, that was 0. The right bound, I forget what that was at. I think it was 10. So remember, those always correspond to your domain, the x min and the x max, right? So let's see, we press enter there, enter again. And there we go. So interpret these numbers. 129.516 is how high this thing got. And that height was achieved at 1.469 seconds, right? So we can move this out, move this in. We can answer the maximum height question, right? So this is going to be 129.516 feet. And that occurs at 1.469 seconds. This was your y coordinate. This was your x coordinate. So we need both of those. Now they're talking about, okay, when does it hit the ground? When is it 20 feet off the ground? What's the domain? All right. Well, E and F are going to kind of go together. Let's deal with D. So 20 feet off the ground, remember, this is going to be a upside down parabola. And we're going to introduce a line, a horizontal line through 20, and we're going to see where it hits. Now, this thing is only going to hit once because it started on top of a 95-foot building. So we started up there, we threw it off, and it's going down. It's only going to hit 20 once. I know the parabola is going to hit over here, but this is not really in the domain of the problem. It doesn't really make sense in the context of this problem. So we'll keep that in mind as we transfer back over to the TI. There we are. We're going to go back to y equals. We still have the original thing typed in there. So we're going to go down and type in y equals 25. Or no, it was 20 on this one. 20. And we're going to press graph, and we see it introduced there. There's an intersection point right there. Now, if we want to find that exact intersection, we do second, trace, go down to option 5, the intersection. First curve, second curve. Remember, there's only 2 curves on here, so we could just press enter twice and then guess. And there it is, right? So it achieves 20 feet at 4.085 seconds. So yeah, so it was 4. I think my stylus went dead here. 1 second. This thing's giving me attitude since I got it. Green means go. Come on. All right. Come on. Loggy pen or whatever that says. The loggy Latin for garbage. It must be because this thing's not working. Okay, we're going to disconnect that. And what did we say? We said at 20 feet, or that happened at 4. Oh, maybe because I was writing with the eraser. That's probably why. Whatever. You didn't see that. 4.085 seconds. There we go. So we've done kind of 2 of the 3 sort of functions on our calculator that we have to be familiar with, right? On C, it was finding the maximum, right? That's one thing that we'll have to learn how to do or know how to do. Part D, it's how to find an intersection. We'll have to know how to do that. And again, that's not just for this year. This is also for next year. You're going to do a lot of this stuff often. And then the third and final function you need to know how to do is how to find an x-intercept. When does this thing hit the ground? So, back to the TI. And again, we're talking right down there. When does it hit the x-axis? Well, I'm going to go second, trace, and I'm going to go down to number 2, the 0. And then we have left bound and right bound, right? So we want the left bound to be above the x-axis, so that's about good. That's clearly above. And then I want to shift it down, my cursor down, so it's below the x-axis, and you can see it's at 4.3 comma negative 4.3, so it did dip below, so we could press enter there. Guess, and then there it is, right? Remember, if you ever see an E and some stuff like that, that means 0. And it looks like this happens at 4.314. 4.314, it hits the ground. Okay, I thought this came back to me, but it didn't. Okay. 4.314 seconds. Okay, so finding the max, finding the intersection, finding the 0. This is a great little summary of the 3 things you need to know how to do in this skill on the calculator and for the future. F is highly connected here. What is the domain? Well, remember it was 0 seconds because going below 0 wouldn't make sense in the context of this problem. X is in the middle. And it hits the ground after 4.314 seconds, so that's where it maxes out at. I do want to underline these inequality signs because it does make sense to talk about 0 seconds and 4.3 seconds because it's time. So 0 seconds, 4 seconds, that makes sense. Unlike the last couple problems from the previous worksheet where like the 0 and this number represented a length that couldn't possibly happen due to the amount of materials. So there we have that. This was added in here so that I could have kind of some proof that you can do it on your calculator. That was kind of the goal with this. If you on this one you don't have to, but on the other one. I think there's one more problem where they ask you to do it. And I'd ask you to do your best on that. So the problem I'm talking about is right down here, letter E. So when you attempt this problem on your own, see if you could take a picture of your calculator screen and put it in this box. If you're having trouble or you don't know how to do that, it's okay, but I would like to see if you know how to do it on your calculator. All right, so that's what G is. We won't do that now, though. H, oh, okay. If you had the opportunity to safely throw a piece of food off a building, what would it be? I guess it's up to you. I guess I would choose carrot or carrots, right? Because if you're going to throw one, why not throw more than one? I would probably do carrots because I think it would be the least eventful thing. I think it would be the most uneventful food to throw off a roof. I feel like it would stay intact, wouldn't cause too much of a scene. That's what I'm all about. Let's go down to number 2. We got, okay, so it's another one of these. We're fitting a rectangle underneath a curve, right? So we're used to having curves where it's like half a parabola or even a full parabola, but they're switching it up here a little bit. They're doing a semicircle, right? And the equation of a semicircle is the square root of this stuff right here. All right. And let's see what they say. They want to say, okay, write the equation that models the area of the rectangle as a function of x, given that x is the coordinate of the lower right corner of the rectangle. All right. See if we could explain that. We have a particular rectangle highlighted in red, and we see it there, but it's not obviously the only one that could fit underneath here, right? The rectangle that would have, that would look like this, going from there to there to there to there to there, that would also fit underneath, right? A kind of a shorter one. You could do kind of a taller one like that, right? We're talking about every single rectangle I could fit underneath this semicircle. So just imagine these corners, right, kind of spreading up and down along the edge of the circle, creating new and exciting rectangles. So when we name functions, if it's an area thing, we usually call it a of x. And what we're going to have to do is we're going to have to get a length and a width, right, for any rectangle, not just the one I see here, because obviously I see that the width is 4, right? But I'm talking about what if I had just some general rectangle that just went some distance that way and the same distance that way. Maybe they're at 2.5, maybe at 3, 4.1, who knows, right? Well, I could call that, right? I could call that length from here at the origin to wherever I land, I could call that x. But if I go x in that direction, I got to go x in that direction, which means that my width, and we've seen this before, I think it was on worksheet 1, I think, the width of the general rectangle is 2x. So don't get caught up in the example they give you and say it's 4 or something. It's 2x in general, because in this red one, the x is 2, so 2 times 2 is 4. (2x), that's my width. Now I need my height or my length. So we're talking the distance from wherever I land up to the curve. Up to the curve. Right there, right there. Like, where would that be, right? Well, that height is y, because it's always x, y, but we don't want to call it y. We want to call it what y is equal to, the square root of 25 minus x squared. And by the way, this is how you graph a semicircle on your calculator. You do this one, and you do the negative version of this, and you get the whole circle. Because imagine solving for this, or like squaring both sides, you get y squared equals 25 minus x squared. Move the x squared over, that's the equation of a circle. So we said it was y, but we don't want to say y, we want to say what y is equal to. 25 minus x squared. All right. And there we go. So, and if we're confused by it, we could label the parts. This is my width, W. This is my length, L, or height, H. So it's the first one I think we've seen with a square root in it, so a little more exotic. what is the maximum area? So we're going to break out the TI for this one. So we're going to type in this into y equals. Get rid of the stuff from the previous problem, clear all that out. And we have 2x times the square root of 25 minus x squared. And we're going to press graph, see how that looks. Okay, well that's not too bad. We could probably shrink the window a little bit, although you could do all your calculations from this screen just fine. But let's make it look a little nicer. I'm going to go to Window. My X-min, Y-min, those look great. My X-max, well, let's think about that. The X-max is going to be part of the domain. I can't put in any number bigger than 5, right? Because if I go bigger than 5, like 6, 7, 8, whatever, I'm not going to be able to fit underneath this semicircle. So that'd be no good. So keep that in mind. We can't go bigger than 5. So my X max, I could shrink that down from 10. I could go to 5. The Y max, well, to fit underneath a, a circle of radius 5, we're probably talking pretty small numbers, but we can confirm by going second graph and taking a look at the numbers that we get. 9 point something, 18, 24, 24, and we go back down. So we're talking numbers under 30. So we could probably go Window, put Y max at, instead of 150, let's go 30. And you can see this is a tighter fit to the window. It looks a little nicer, a little classier. All right, so we got maximum area. So even though it's not a parabola, specifically, you're gonna go second, calculate maximum, just like you normally would. So that's number 4. Left bound was 0. Right bound was 5. Guess. And we're up there. All right, so the biggest area is 25 units squared, and it occurs when the lower right-hand corner, because that is what the X represents in this problem. You could read the instruction line again. That's what it says. The lower right-hand corner is going to be at 3.536. All right, so we'll keep those numbers in mind. And, okay, so what did we say for area? Well, that's going to be 25 units squared. So that'll be the answer to that one. And now we want the coordinates of the vertices of the rectangle with the maximum area. All right, so that means the corner points. There's going to be 4 of them. Over in this picture, let's see if we could describe them. They said, or our calculator said, from the maximum point we found, the maximum rectangle that could fit underneath this curve can be found when you have an x coordinate that is 3.5 units away from the origin. So we're talking like right there. And if you go 3.5 that way, you got to go 3.5 that way. We go straight up, straight across. That's the rectangle. That is the biggest rectangle you could fit underneath that curve. All right. So what are the coordinates of the corners? Right. So we're talking up here, down here, up over there, down over here. Well, this on the x-axis, like we said, remember from our TI, it's going to be at the coordinate 3.536, comma 0. 3.536, comma 0. 536, comma 0. Now, remember, if you go 3.536 to the right, you got to go 3.536 to the left. So we're going to have negative, its matching partner here, 5, 3, 6, comma, 0. So we just did that one and that one. The two lower right are the two lower ones. Now we need to find the upper right and the upper left. Let's deal with the upper right. The upper right corner is going to come from plugging 3.536, the positive version, into this, the square root of 25 minus x squared. Let's do that. So just in the calculator part, we're going to do the square root of 25 minus, and we're going to do minus the x coordinate squared. So remember that was 3.536, was that? Yeah, that was it. And squared, like that. Let's see what we get out. Almost the same thing, 3.535. So it's a kind of a square. Or no, it's not a, it wouldn't be a square. It'd be a rectangle where the length is double the width. But so let's keep that in mind, 3.535. So we have a coordinate at 3.536 on the x, and then comma, the thing we just calculated, 3.535. Top left corner would be at negative 3.536, comma, and it'll be up at same coordinate 3.535. And just like that, we have completed this problem. So not only do we have to get that equation, right, we have to interpret the results. What do they mean? What does the x and y mean? That is going to be kind of the goal here. All right, so we did half of that together. I do apologize for not being there. I do feel bad about that, especially during this unit, or this skill in particular. But if we could, guys, for Monday, if we could finish the last two problems, they're highly related. They're a lot like the last couple on worksheet 2, right? The only difference is we're building it along the river like usual, but there's an extra little fence in between. It kind of makes the letter E. That's on number 3. And on number 4, same thing, but now not just one little fence in the middle, 3 fences in the middle, plus the end caps there. So see if you could generate that, get the proper dimensions, get the max area, and again on letter F here, and letter E here, see if you could take a picture of your calculator, the screen of it, all right? And what we're going to do is once you have that done, you could turn it on in to, what's it called? Polynomial Modeling Worksheet 3. Okay, so that'll be due by Monday, but there's only 2 questions. You got the rest of the period. This video currently is 48 minutes long, so you should have plenty of time. If you finish early, you can't leave, okay, because there's a sub and you got to be there the whole time. So if you finish, just, contemplate on your life until 3:25, and I'll be back on Monday to help you out with this and any questions you might have on worksheet 2. So we'll circle back to that if we need to. All right, and I will see you on Monday.